Hi everyone, my name is Stuart Grant. I am a third year PhD student in the Systems and Networking group, and today I'm going to present some work that I've done with my advisor, Alex Snoren, on in-network contention resolution for disaggregated memory. So to begin with, I've got a primer on disaggregated memory. So it's an architectural paradigm that is a departure from a traditional monolithic server architecture. So what is that? Well, a monolithic architecture would be one in which the CPU, memory, disk, potentially all like accelerators are all co-located in a single box. And this is going to be the vast majority of any computers you've seen in the past. A disaggregated architecture is one in which all of these same resources are separated over a network. And why would you do something like this? Well, the biggest advantage is scalability and composability. So with all of the resources separated over a network connection, you can essentially create a server that has, potentially hundreds of CPUs just by reconfiguring the way that your network is strung together. There's also big savings in terms of density and in terms of power. So one of the biggest costs in data centers today is actually cooling, and one of the advantages that disaggregation would give in the data center context is that something like a CPU, which generates a lot of heat, can be cooled separately from resources like memory that don't generate a lot of heat. And so that degree of concentration and specialization at the data center level is one of the reasons people are pushing for disaggregation. But there's also challenges here, and the biggest challenge, in my opinion, is latency. So in some cases, this is not prohibitive. So things like SSDs, so solid-state hard drives, have already been disaggregated and deployed at large scale. And that's because reading and writing to SSDs has a latency comparable to that of going over the network, which is roughly 1 microsecond. That, however, is a pretty high cost in comparison to accessing local memory. So the biggest challenge really in resource disaggregation is this network separation between a CPU and what would have been its local memory now being over a network. And why is that a problem? Well, the biggest issue is in terms of contention. So 20x cost read and write, that's pretty bad already. But what about when you have multiple CPUs that are all reading and writing to a shared location and you want consistency? This is really bad, because even something like implementing a spin lock on remote memory is going to be very, very expensive. So what I have here is a chart that shows the performance degradation of a key value store, Clover, which is already optimized for remote memory. It works under the assumption that there are no remote CPUs, and it has a pretty smart algorithm for opportunistically optimizing both reads and writes. However, it still suffers significantly. So on the right, what you see is different YCSB benchmarks, C, B, and A, where C is 100% reads or 0% writes, B is 5% writes, and A is 50% writes. And so at a 50% read-write ratio, there's a 5x performance loss. And again, this is using state-of-the-art techniques. So the nature of this performance degradation is that there is no serialization. In order to have atomic access to a shared region, there are some very expensive operations that need to be run in the network, specifically compare and swap operations. And this is because there's no serialization with a remote CPU. Okay, so in this work, we make the observation that all of these operations that are transiting the network are actually serialized anyways. They're serialized on the egress port of a top-of-rack switch as they prior to arriving at any memory server. And because they're serialized, we can actually deal with this contention in the network. So this is the key takeaway of what we're doing. We're taking the responsibility that would be given to a CPU on a remote server, and because we still have a little bit of compute in the network, and the fact that all of these operations are serialized, we're going to take advantage of that. There are some significant challenges to performing any kind of computation in the network. The biggest one is that switches are intended for packet forwarding and not necessarily running programs. There's a lot here. So one of the big ones is that the SRAM that is on a packet switch is at an extreme premium. There's like 64 megabytes of this in the best case, and it's again really intended to buffer packets. It's not really meant to store things. So if we're going to do any amount of storage on a switch, it has to be at a minimum, and it has to get you a big benefit. And on top of that, adding a switch to your program not only is conceptually quite complicated, but it really increases the failure risk. So we want to make sure that anything we put on the switch we don't necessarily rely on. Also, it's got a restrictive programming model. So these aren't like x86 chips. These switches do have x86 CPUs on them, but they're not in the data path. And so anything that we're going to write that's going to touch every packet has to be written in P4, which is pretty restrictive. So we have only a few operations that we can play with, and it has to be very, very minimal. And then for those of you who are quite familiar with this, it would be very easy if we could do something like establish RDMA connections on the switch, but we can't here because we would need specialized hardware for that. So all we're going to see is in-flight packets. And so without getting into too many of the details, we've implemented an algorithm which runs on a programmable switch that is essentially deals with the read and write contention by acting as a proxy to maintain data structures in remote memory. And so we've implemented this on Clover, this key value store that I mentioned before. And what we've done is totally interposed on its protocol. And we keep a cache in network of the most relevant metadata when there are conflicts to shared regions. So it maintains a key value store, and at a very high level, what we're doing is whenever there are two concurrent reads to the same location, we arbitrate them and make sure that both of the writes succeed as if they were done from a serialized CPU. So even though it's concurrent, we just sort of deal with the conflicts in the network, make sure all the writes succeed. And so all of the performance collapse that you would have seen from needing to do retransmits are going to go away. So we've tested and implemented a prototype of this. What you see on the right here is, in red, is the default performance of Clover in our experimental setup. On the y-axis, you have thousands of operations per second, and on the x-axis, you have the number of threads. And threads here are going to be a proxy for the amount of concurrency. So with 2 threads, there's not a lot of concurrency. At 64 threads, these are 64 threads all making concurrent accesses to shared regions. And so what you see in blue is the performance with our middle box turned on. And as the amount of concurrency increases, so too does the performance benefit that we see. And at 32 is sort of the last point before we really start to take off. At 64 threads, when we're running our algorithm on all of the metadata that Clover has, we see a 1.4x improvement. As I mentioned before, the resources on the switch are very constrained. And so what we've done here is shown that we can operate with a relatively small amount of memory and still see a performance improvement. So again, on the y-axis, you see thousands of operations per second. And on the x-axis, what you see here is the number of keys that we're caching. So this is, again, a key value store, and some of these keys are hot. So when we cache just the hottest key, we see a pretty steep performance improvement. And if we cache only the top 8 keys, we see 1.35x. And so that's only 128 bytes, which is definitely within the 64 megabyte limit that would be on a commodity programmable switch. So there's significant benefits to be had from only using a small amount of cached information here. Okay, so that's it for this talk. If you have more questions, please message me or come and talk to me. Hopefully I've convinced you that the network caching and arbitration can help deal with RDMA read-write conflicts. We see 1.4x throughput improvements with these early experiments with full caching and 1.35x with just 128 bytes of the hottest keys. My personal page is stuartgrant.ca. Our code right now is totally open source on GitHub /WontonSolutions/warm. Thank you.